Greetings and welcome to the Introduction to Astronomy. In this episode of New Discoveries in Astronomy, we will talk about how astronomers detected a twisted magnetic field surrounding the outflow from a newborn star. So let's get started. How can astronomers map a magnetic field they cannot actually see? Magnetic fields may play an important role in the formation of stars, but observing those fields directly is extremely difficult. Instead, astronomers have to look for ways that an invisible magnetic field leaves its signature on matter that we can detect. And the nearby star-forming region, NGC 1333, astronomers have now measured one of those signatures with remarkable detail. NGC 1333 lies within the Perseus molecular cloud, about 960 light-years from Earth. Within this active stellar nursery is a very young double star system called NGC 1333 IRAS 4A. Young stars grow by pulling gas and dust inward from their surroundings, but at the same time they can send some material back into space through narrow jets and broader outflows. That creates an important problem. For decades, theoretical models have suggested that magnetic fields have become twisted around these outflows as the young stellar system rotates. But actually resolving that magnetic structure close to a forming star has been extremely difficult. To investigate the field, astronomers use the Atacama Large Millimeter Submillimeter Array, or ALMA. Rather than trying to photograph the magnetic field itself, ALMA measured something much subtler: faint polarization in the emission from carbon monoxide gas within the outflow. Polarization describes a preferred orientation in the electromagnetic radiation reaching us. By carefully measuring that orientation across the outflow, astronomers could infer information about the geometry of the magnetic fields threading through the gas. The new observations provided roughly 30 times greater resolving power than earlier measurements, allowing researchers to examine magnetic field structure only a few hundred astronomical units from the young star. In other words, the magnetic field remained invisible, but its influence on the radiation gave astronomers a way to map it. And when the researchers reconstructed that magnetic field geometry, they found something theorists had predicted for decades. The magnetic field was not simply running outward with the gas. Instead, it showed a strong toroidal structure. That means the field wraps around the outflow axis, somewhat like rings surrounding a tube. The gas moves outward while the magnetic field is oriented largely around it. The researchers measured field strengths of a few thousandths of a Gauss, small by everyday standards, but significant across the enormous scales surrounding a protostar. Most importantly, the observed geometry closely matched the structure predicted by models of magnetically driven stellar outflows. That matters because young stars face another fundamental problem as they grow. The material falling toward a forming star carries angular momentum. If the system cannot redistribute or remove enough of that angular momentum, continued growth becomes difficult. Magnetically influenced outflows provide a mechanism for carrying material and angular momentum away from the forming star. So these observations are not simply a picture of an unusual magnetic shape. They provide direct observational evidence that the magnetic fields have the kind of geometry needed to help organize protostellar outflows. The researchers also found a relationship between the field's twisting and electric currents in the gas, potentially giving astronomers another tool for studying magnetic fields in star-forming regions. There is something especially useful about this observation from a scientific point of view. Astronomers cannot see a magnetic field directly. Instead, they measure how light from matter responds to its presence. From polarization, they infer orientation, and from many of those measurements together, a larger structure emerges. An invisible field becomes a testable physical model because matter carries its signature. So that concludes our discussion on ALMA reveals a twisted magnetic field around a newborn star. We'll be back again next time for another new discovery in astronomy. So until then, have a great day, everyone, and I will see you in class.